Dear students, this is the revision for your class test. Let us recall some theorems which will be required for further questions. The theorem says if the series summation an, where n goes from 1 to infinity, is convergent, then limit of an is 0. But the converse is not true. The second result, which is known as p-series test, it says the series summation 1 upon n raised to p, where n goes from 1 to infinity, is convergent if p is greater than 1 and is divergent if p is less than or equal to 1. The harmonic series is the series 1 plus half plus 1 by 3 onwards. That can also be written as summation of 1 upon n, where n goes from 1 to infinity. The alternating harmonic series is defined as 1 minus half plus 1 by 3 minus 1 by 4 plus. So it is the harmonic series with alternate signs plus minus, which can also be written in the notation summation minus 1 raised to n plus 1 upon n when n goes from 1 to infinity. Now some objective type questions which are important for your class test are, I am reading out the answers. The questions will have multiple choice and you have to select the correct option. But in this video I am reading only the answers and explaining them. Now if the limit an is 0, then the series may not be convergent. Just now we saw the theorem, the converse is not true. So applying that, you have if limit an is 0, then the series may not be convergent or may be convergent. You would never know. Then the series summation minus 4 upon n does not converge. This series is a kind of p series with p is equal to 1 and therefore it is not convergent. That is divergent. The series minus 2 upon n square converges absolutely. Here it is a p series with p is equal to 2 and that is why it is absolutely convergent. And there is also a theorem saying if a series is absolutely convergent, then it is convergent. So both the statements are true. The series given by this is absolutely convergent, so it is convergent. The next question is if an is 1 upon n square. Now when I write an is equal to 1 upon n square, it is a sequence. Then the sequence an, as you know, 1 upon n square sequence is convergent, converges to 0, and the series, if you talk about the series, it is the p series with p is equal to 2. So p is greater than 1, so the series is also converge. And that is why the correct answer is the series, the sequence and the series both are convergent. Next is the series minus 1 raised to n. If you put the values of n here, it is the series minus 1 plus 1 minus 1 plus 1. If you take even number of terms, then the total is 0. If you take odd number of terms, then it is minus 1. And that is why when I say series, it is actually a sum. So the sum of this series oscillates between minus 1 and 0. That is the correct answer. Then you have the geometric series. We have used it in so many examples, as you know. It is 1 plus r square and it is convergent if mod r is strictly less than 1. Please note it is strictly less than 1. And it is divergent if mod r is greater than or equal to 1. Then you have again the harmonic series and it is conditionally convergent. This is alternative harmonic series and it is conditionally convergent. The next statement is if limit of 1 upon n is 0, what can you say about series 1 upon n? Is it convergent? The statement says if limit 1 upon n is 0, then series is convergent. But the statement is false. Because again this is a p series with p is equal to 1, so it is divergent. That is why this statement, please note the statement again, if limit 1 upon n is 0, then summation 1 upon n is convergent, the statement is false. Please note that. Now you have two tests which we have done almost at the end of the lectures. One is ratio test and the other is root test. The ratio test, the statement is limit of, you have to take the ratio an plus 1 upon an. You have given the series summation an, you take n plus 1th term, divide by nth term, take the ratio, modulus, and take limit n tending to infinity. So what is it? What is L? Limit of mod of n plus 1 upon n, an, as n tends to infinity is L. If L is less than 1, then the series is absolutely convergent and hence convergent. If L is greater than 1, then the series is divergent, and if L is equal to 1, then the root ratio test is inconclusive. So you cannot conclude anything. Similarly, you have the root test. Here the value of L is defined as limit of nth root of modulus of an. And then the remaining part of the test is similar to that of the ratio test. If L is less than 1, the series is absolutely convergent and hence convergent. Greater than 1, divergent, is equal to 1, inconclusive. So these are the two tests. There are some examples which I have done in the tutorials and the lectures. Please revise them. No proofs of the theorems will be asked in your class test. All the best.